Hello everyone, we are Giuseppe Lamanna and Anni Domenics Arias from Lutech. In this clip, we will briefly present a research activity in which we investigated hybrid quantum classical convolutional neural networks and compared them to their purely classical counterpart. Recently, convolutional neural networks have become a cornerstone of computer vision. However, they still face significant challenges like overfitting and a high number of parameters, leading to cumbersome memory usage and extended computational times. Recently, quantum computing technology has advanced rapidly and might be an attractive avenue to overcome these challenges. Recent studies have explored the integration of quantum computing with classical CNNs, suggesting that a hybrid quantum classical model may offer practical advantages. In this context, our research questions were: 1. How does the prediction accuracy of a hybrid CNN compare to a purely classic one? 2. Are there any computational advantages regarding time consumption and memory usage? 3. Given the cost and availability of quantum computers, researchers often fall back to simulators, but actual quantum computers are affected by noise. Thus, we simulated the noise and tested our model in such conditions to predict how a real quantum machine would behave. We experimented with a simplified dataset of 2D 3x3 grayscale images representing Tetris bricks, labeled with the S, L, O, and T letters. This dataset was chosen for its simplicity and relevance to the computer vision, as it allows us to focus on the hybrid system's performance in a controlled environment. The grayscale images here are plotted using matplotlib as pseudocolor images, so the pixels with higher values are represented with brighter colors. Let's start describing the model with a brief overview of how a classical convolutional neural network works for a classification task. A CNN typically has two main components, convolutional layers and fully connected layers. In the beginning, convolution operations map the starting image to a new representation using a sliding window called filter, composed of a determined number of learnable parameters. The resulting image is then fed to a further convolution and so on for a fixed number of times, resulting in an information-rich representation of the image, which is then passed to the final fully connected layers that perform the classification. Similarly, a quantum convolutional layer acts on the input image by filtering it. However, unlike its classical counterpart, it does so by running a variational quantum circuit that maps an initial quantum state of an arbitrary number of qubits to another. In our case, this happens in two phases. First, the n-pixel values of each sliding window are mapped into an n-qubit variational quantum circuit using a specific arrangement of non-trainable parametric quantum gates called feature map. Specifically, we used Qiskit's ZZ feature map. The second part of the variational quantum circuit is usually called ansatz and comprises trainable parametric quantum gates. In this work, we adopted Qiskit's real amplitude ansatz. We ran the variational quantum circuit several times and measured the computational basis on the output quantum state to estimate the 2 to the n probability coefficients. These 2 to the n real numbers are then fed into the subsequent classical layers. The number of trainable parameters in the ansatz can be arbitrarily chosen, so one could, in principle, try to obtain better performance with fewer parameters. Parameters are updated using the classical mini-batch gradient descent algorithm. We employed the parameter shift rule to differentiate the quantum filter's output. The built model was trained in Python using the Adam optimizer on the proposed dataset, and the classification accuracy was measured. Our results show that the hybrid system outperforms the classical one in terms of classification accuracy, even when equipped with fewer trainable parameters. Moreover, under a variable amount of the polarizing noise, the hybrid system shows resilience, potentially outperforming the classical counterpart, while under up to 7% of the polarizing noise. This robustness under challenging conditions is a testament to the hybrid system's potential for real-world applications. In conclusion, the hybrid quantum classical model performed equal to, if not better than, the classical model, requiring fewer parameters and showing an acceptable resilience to noise.